Throughout the 2018 to 2019 academic year, the PPMS MAPS team has been focusing on researching about the protein aquaporin, specifically the variant AQPZ, which is found in E. coli. Many Indians face hardships in finding clean water. Many families contract waterborne illnesses because of consumption of contaminated water. We believe that the MAPS team can help India by finding new ways of applying biomimetic membranes using the protein aquaporin to filter water.
This is not only a water crisis, this is also a sanitation problem because only 33% of Indians have access to traditional sanitation. And in the present right now, a third of the groundwater systems around the world have been used up. And by 2030, water scarcity will displace 24 to 700 million people. And by 2040, there will be no water in most parts of India. And if this continues, water crisis will only get worse.
So to solve this transcending problem, we will implant aquaporin from E. coli into artificial membrane. And we took aquaporin from E. coli due to its abundance in nature and due to it being easy to harvest. And aquaporin is made out of 6 helices, which are the spirals that you see over at the model, and 2 half helices. And they join to form a tunnel, which forces through the water molecules single file and gets rid of any other foreign substances such as salt, bacteria, or hydrogen ions, which can make the water very basic. And the aquaporin also has 2 NPA motifs and an arginine selectivity filter, which we will get to next.
So as mentioned previously, this is our model of the aquaporin we used. So there's 2 major points as mentioned earlier, the aromatic arginine selectivity filter and the NPA motif. These are both made up of amino acids. For example, the arginine selectivity filter contains, it contains arginine, which is a positively charged amino acid, which is able to help repel hydrogen ions, which also prevents the water from becoming acidic. And then the other 2 parts help weed the water down by forming weak hydrogen bonds and weeds it down to the next part, the NPA motif, where the NPA motif helps weed it down one by one, so it's able to prevent anything else from going in. We have asparagine, which is one of the main parts of the NPA motif. It is focused on because it is one of the hydrophilic parts of the NP motif, and as said earlier, it guides it down and to our result.
Okay, so as you can see on this first graph here, it measures the water productivity of several different filters. Now, water productivity is defined as permeability per unit driving force, which means that this graph measures the speed that the water travels through a filter. As you can see on the graph, AQPZ has the highest water productivity, which means that it travels fastest through the filter, which is best. As you can see on the second graph, this measures the pore diameter of 2 different aquaporins and an aquaglyceroporin, GLPF, which is an aquaporin that lets glycerol and water travel through. So as you can see here on the graph, GLPF has a larger pore diameter than AQP1 and AQPZ because it has to have a larger pore diameter to let in both glycerol and water, while AQPZ and AQP1 have smaller pore diameters to let in only water. However, AQPZ has a smaller pore diameter, the smallest pore diameter out of all of them, which makes it the best. In conclusion, AQPZ is the best aquaporin used for water filtration, and it can definitely help save lives. Thank you.